I am Greg Miller, and this is The Black Donut, presentation for CAD 299 Supervised Study at Northern Virginia Community College. My advisors for this project were Professors James Connick and Colin Jacob. This is our Sun. Crammed with trillions of tons of superheated gas, it is the center of our solar system. But there is more to the Sun than what is on the surface. Like an ogre, the Sun has layers. At the core, nuclear fusion powers the Sun. Our Sun contains an enormous amount of matter, 1.98 times 10 to the 30 kilograms of it. All this material, located in just one area, results in a gravitational pull that reaches halfway to the next solar system. The immense gravity of the Sun is constantly trying to crush it down into a little ball. The forces trying to blow the Sun apart are equally powerful. Nuclear fusion, the inverse of the nuclear fission of our atomic bombs and power plants, is the creation of new elements by fusing together atomic nuclei under great heat and pressure, releasing their energy into the star. There is another small force keeping the Sun from collapsing in on itself: centripetal force. The effect is negligible due to a relatively slow rotation, but it is still present. At the end of its life, the Sun will have used up all of its nuclear fuel. Then the forces holding it up will come to an end, and it will swell up into a red giant and then collapse into a white dwarf. An interesting thing to note is that the Sun will be spinning much faster as a white dwarf than it did as a yellow star. This principle is identical to an ice skater spinning with arms outstretched. As he pulls in his arms, he spins faster. This is called conservation of momentum. Our Sun is a fairly average star of a fairly average size. A star much larger than the Sun won't turn into a white dwarf, but will instead have so much mass that it will become a neutron star. A neutron star is so dense that the electrons of its atoms have merged with their protons, forming an object composed nearly entirely of neutrons. This object, starting from a much greater mass and volume, shrinks down to the size of a small city. A neutron star spins very fast, many times per second. Such speed would send us all rocketing off the surface of the Earth. Some stars out there are truly Titanic. When these stars die, they all die young, and they do not die quietly. What remains of the death of a very large star is a black hole, a very small packet of material, theoretically of infinite density. But what if it isn't exactly infinite? The gravitational pull of a black hole is the result of a great deal of material, mass, crammed into a very small space. That small space is represented by the radius of the volume of the object. If you crushed the entire planet Earth down until it was the density of a black hole, and then stood on a fixed platform in space exactly where you are now, you would feel the effect of its gravity exactly as you do now. Newton's law of gravitation demonstrates this. But there's more in there. The equation that describes gravity approaches an asymptote, a limit, which means that it never quite reaches infinite density. After all, infinity is functionally meaningless in physics. You can't divide by zero. Let us suppose that R can get very close to but never actually equal zero. Let us suppose that there is a state of density beyond which a black hole no longer crushes matter down. In that case, the density remains constant even as the black hole consumes more. From an enormous mass and radius to the same mass but very small radius, momentum must be conserved. With increased velocity comes an increase in centripetal force. In addition, as material falls in, they add their momentum, both their mass and velocity, much affected by their approach to the black hole. So, how fast can it spin? Let us presume the obvious, that just shy of the speed of light is the upper limit. Gravitational acceleration on Earth is 9.8 meters per second squared. If the Earth spun at the speed of light, the opposing centripetal force would be 1.4 times 10 to the 10 meters per second squared. Our typical neutron star with a diameter roughly equal to Brooklyn, New York, might spin 50 times per second, not quite enough to overcome its enormous gravity of 1.34 times 10 to the 8 meters per second squared. However, at the speed of light, that neutron star would experience 1.18 times 10 to the 13 meters per second squared in centripetal force. That is more than enough to rip the star apart. An interesting question comes up. If the centripetal force matches or just barely exceeds the gravitational force, what might a black hole look like? Spinning very fast, it might look like a donut, a torus in math speak. If this were possible, it would probably only be the case with very large black holes, such as those found in the centers of galaxies. With a largely fixed density but increasing mass and velocity, other forces come into play. This could happen gradually, or it could be sudden. The former could transition like this, stopping along the way, depending on the degree of the ratio. The latter makes for an interesting case. Consider this empty pitcher resting on a pivot and a block. Its centroid, its center of mass, is behind the pivot, so it stays upright. When it fills with water, the centroid of the water is forward of the pivot, and so it all spills over. Not gradually, but catastrophically. In the same way, an infusion of just enough angular velocity might tip over the black hole, spilling it into a black donut. As the torus spins, its gravitational forces act as one from all directions in the plane to pull at spacetime, ripping open a pocket of null space. That is, there would be a region at the center of the torus where space isn't, and that's important. Particles and objects orbiting this torus at a distance would not behave very differently than were they orbiting a sphere. However, particles orbiting very close are another matter, in part because it takes a peculiar particle to exist that close to the anomaly. Its orbital path would routinely pass through the center of the torus. This is significant in that this particle, assuming that it returns from the venture, is either traveling through a very squashed region between null space and the torus, or is entering and exiting the null space routinely. This behavior is reminiscent of peculiarities in quantum mechanics. If we assume that the donut isn't quite so plump, that it might instead resemble a thin rubber band. A rubber band under tension, trying to pull itself apart and trying to keep itself together. Under many competing forces, the string may buckle in order to stabilize, translating wave motion around the object. The effect of this should be observable in surrounding material. Like the orbiting particle, this trait is also reminiscent of the behavior of quantum strings. There may be some connection there between the behavior of the very, very, very small and the very, very, very large. So let's review. The radius of a black hole is never zero. Centripetal force on a black hole is significant. Because the material is very dense, there may be a ratio of gravitational force and centripetal force that moves the material of the black hole away from its center. The force pulling on one point in every direction on a plane would distort and possibly rip a hole in spacetime. Particles orbiting a torus closely may travel in and out of its hollow center. This behavior is reminiscent of some behaviors in quantum mechanics. Just as we can treat the mass of a spherical black hole as a single point, we can treat the mass of a toroidal black hole as a string. And lastly, because of the material's density, angular velocity, and the consumption of particles on the outside edge along its plane, the black string may vibrate. The effect of this vibration, of a changing distance from the surface of the black hole to an object, should be observable in material nearby. It is entirely reasonable to suppose that none of this is actually true. It is possible that nature cannot find a way to do this. So, does this happen or not? I don't know, but that's okay. I started this exploration out of a short bit of curiosity. I wanted to know if you could create a region of artificially dense space that could slingshot a spacecraft before the anomaly evaporated. It seemed like a donut-shaped anomaly would be better, since that permitted a linear path to the center rather than an angled path around the outside. That thought led me to a series of what-ifs, which in turn led me to the black donut. A few days after I chased this rabbit down the hole, my research on it led me to Roy Kerr and the Kerr black hole. I had stumbled upon the same principle he described 60 years ago. He had some amazing insights about this and other principles in physics. You should read about him. I'm glad my curiosity helped me discover him. Mental exercises like this are valuable, even when they yield work that has been done or come to no correct or useful end. It teaches us to explore, to understand, and to be both fair and critical, both of ourselves and of others, while maintaining the kind of unfiltered creativity that we enjoyed as kids. If you have any questions, comments, or would like to see what else I'm up to, feel free to email me or to check out my blog where I talk about this in greater depth. Just look for the Black Donut. I also vainly try to solve the world's problems and complain about rubber duckies. Thanks for watching. What? You want to see that supernova again? Alright. See you later, folks.